So I write my exams to be done within a half an hour if you know what's up. You talk to anyone in here who's taken my exams. They're much easier than anything I've given you so far, right? Is this true? Like all the suffering in my classes takes place in private. I don't want to see you suffer. Because if you suffer and I have to grade that, I suffer. I don't do that. So, trust me, it's usually like 5 problems. Now that could be multiple parts, like a couple things, but like if it's more than 5 pages, I don't know what I've done. I've done something wrong. And that means 5 pages with space for you to like fill stuff in. That is like, does that feel better?
Yeah.
Cool. Any other questions? No. But I strive for, I feel someone will walk out of here at the half-hour mark. And then Monday is like, just come and practice and work and talk and we'll consult. This is the last new thing I'm going to talk about today. Does this sound good? Cool. So I had those new office hours yesterday. They were pretty lonely. What the hell's up with that? Where's my friends? Gotta have these office hours on Tuesday. It's all right, I had shit to do. Okay, so this is our last application. I should have made this the first. Oh, yeah, I got one more thing to tell you. So exam 1 will be next Wednesday, and then we have a week before break. That 1 week before break is going to be a self-contained module of awesomeness. And then after we come back from the break, we won't do it anymore. But I've got this one thing I want us to do that's so fucking cool, so much fun, so beautiful, that we're just gonna dedicate those 2 classes to it, and then go to break. You'll have this over the break to do. It'll be so awesome. You'll be so grateful that you'll have something to fill your time over the break. I'm being completely sarcastic. Orthogonal trajectories. This is geometric and physical and all sorts of cool things. The word geometric came out odd, but that's the way it goes sometimes. So, let's just talk about what do I mean by orthogonal trajectories. Let's say that I have a function y equals f of x. That's my old classic right there. And I have another function, and they intersect somewhere. Where they intersect, the tangent lines are orthogonal. In other words, at 90 degrees to each other. So this is an orthogonal intersection of the 2 graphs. And let me be more precise. The tangent lines are perpendicular. I'm going to introduce that symbol for perpendicular. It's pretty intuitive, right? It looks perpendicular. And so if you've taken linear algebra, you had things that were like perp. You talk about perp spaces and stuff like that. This is just a perpendicular. So our goal is we're going to be given a family of functions. And what this means is that they depend on a parameter that can take on infinitely many values. So, yeah, let me say that. And we're going to find another family of functions. Yes, let's take this word function out. Curves, because they might not always be functions, they might be implicit. Another family of curves, so that whenever one curve from the first family, intersects a curve from the second family, that intersection is orthogonal. And I think probably the best way to just proceed from here is to show. So what we're basically, we are creating an orthogonal family of curves. Create an orthogonal family of curves. Orthogonal is such a great word. Such a cool word. Sounds like you know something when you say orthogonal. So a family of curves. That's the short version. So, yes, now we can go. Good, all that stuff's out of the way. So given y equals cx squared. So c is my parameter, and c will be the parameter in all the problems I give you. So what we're envisioning here is that c varies over the real numbers. Which is that symbol okay for the real numbers? That stands for the real numbers at that capital R. Varies over R. Find an orthogonal family. We're going to use diffie Q, or hopefully, right? So what we're going to do is we're going to get into that family. We're going to break it down into some core information that reflects the slope information. And then we're going to take that slope information, twist it a little bit in the right way, and then pull it back out from the differential form to the normal form, to non-differentiated form, and then we'll have our answer. So let's just go through this. Step 1, differentiate the given family with respect to your independent variable, most likely. So here I'm going to do that, and I'm going to get y prime equals 2cx. Sound okay? So now at this step, this one's nice because everything's explicit here. I've got y equals a function of x, so y prime is nicely exposed. But it might be that I have an implicit function, so I'm going to add in here to solve for y in terms of x, and c. So right here, excuse me, y prime, solve for y prime, might not be needed, like here. But we will do an example next where it is. Step 2, deparameterize that equation from 1. So step 3, regardless of where you're at, this or that, deparameterize. And what that means, i.e., solve the original equation, the original family, solve original family for your parameter, C here. Plug that into the equation from above, and plug that into result from 2, which could also be the same as the result from 1. There might not be anything that happens here, but it's still carrying that down. So in this case, look at my top. We had, I'll write this out so you have nice notes on it. We had y equals cx squared. So c is y over x squared. And I'm going to plug that into equation star. Having trouble drawing a star. Okay, and then so plug into star, and what we get is y prime equals 2 times y over x squared, x. And then simplify here. So now simplify. I guess I'll call that 4. So what we're going to get is y prime equals 2y over x. Does that look good? Tell me, keep an eye on my algebra, please. Yeah, good, all right. So, step 5, so that's just getting down. So now we're at the differential description of that family of curves. Every curve in that family, and actually, let's take a look at what this family looks like. We should have done that right off the bat. What are these things? They're just parabolas, yeah. So here's a positive c. So maybe there's like c equals 1, c equals 2, c equals a half. So let's c equals 1, c equals 2. Here's c equals 0. It's just y equals 0. Here's c equals negative a half. Here's c equals negative 1. And if you're physics savvy or you've had some physics, you might recognize this as lines of force in a magnetic field or something like that, electromagnetic field. Right, it kind of looks like that. It looks like those lines of force, equipotential lines in a magnetic field. And this describes every single one of them. If you take any curve out of this family, any of them, and you grab the x and y coordinates on it, the tangent line can be computed by that formula. So what our tangent line slope? So the slope of this thing, m, is equal to 2y over x, wherever I'm at, if I'm at xy. That's what this means, to do this. Cool, so now we're down at this like kind of core level. Now we have to make the twist. What does it mean to be perpendicular to something? So let's talk about that. If I have a line of slope m, and I have another line that is perpendicular to it, what is the slope of that line? Negative reciprocal, yes. So negative 1 over m. I think, yeah, I think it got said a couple different ways, but yep, negative 1 over m. So this is my slope, right? So I'm going to take the negative reciprocal of that and create a new differential equation. So take the negative reciprocal, I guess that's the word reciprocal, of the right-hand side. And so we're going to get here y prime equals negative x over 2y. Solve this, and that's it. So step 6 is solve the orthogonal DE. So that's what we'll call this. So this is like y prime perp. And sometimes I put a little perp there just so like when I'm thinking about it, I remember that's what this means. A little sub-perp. You don't have to carry it through all the computations because that would be a pain. Hey, could you solve that for me? Because I know the answer is yes. Would you solve that for me? Yes?
What is that RH?
Right-hand side. Good question. Let's find out what's perpendicular to all of those beautiful things. Well, that's the flaming trash can. Maybe not the most romantic image of math. And then once you get this, and don't forget to add a new c in when you integrate. And the c is going to be your new parameter for this family. These will almost always involve separation. Yeah, we getting that? Cool. If you got that, you got it. What do those look like? Anthony? They are not parabolas. Did you have a? Oh, okay, cool. just like
a circle.
Close.
So
Ellipse.
Hyperbole.
It is a conic section for sure. So let's get it. Let's see. This is actually an ellipse, a family of ellipses. Let's talk about family of ellipses because they come up kind of often. So if I have an equation of this form, this is canonical form for an ellipse with center at 0 and at one axis, the x-axis goes out a units in each direction, and the y-axis goes out b units in each direction. So depending on which of those two is bigger, you call that the major axis. The other one is called the minor axis. So this thing looks like this. So what I need to do is get this to understand what this is. I got to divide through by that c. So we're going to have, hey, any restrictions on that c? If we want to have points. Like, what if I put this? What x and y satisfy that? None. Why is that?
Because square doesn't
Has to be non-negative, right? A positive. This side is always positive, or 0, and it's only 0 when they're both 0. So over here, this c, we have to make a little note. When we put this here, note, c must be greater than or equal to 0. And that's okay. It helps to keep track of what's going on here. So when I divide by it, we're definitely assuming it's not 0. So I've got this 2c here, and then this is y squared over c equals 1. That c is a positive number. So now the square root of that is one of my axes. The square root of that one is the other axis, distance. So here, this is x squared over square root of 2c squared. And I'm just writing it in this form so that I can understand what I need to plot. And then this is y squared over square root of c squared equals 1. So why is that important? Well, check it out. The x-axis is bigger by a factor of square root of 2. So the ellipses are stretched out this way. So that's called eccentricity. The amount of how far off the ellipse is from a true circle is called its eccentricity. So this is fairly eccentric. And what it's going to look like, let's say c equals 1. And you might want to just pick some particular parameter values when you're trying to understand these families. When c equals 1, I've got an x-axis that goes out square root of 2, negative square root of 2. Y goes up positive 1 and negative, right, because I'm assuming c is 1, so then this goes to 1, and this goes to negative 1. And I got this ellipse like this. And then every other ellipse is just a scaled version of that. By changing c, notice c is in both of these, I'm just going to get all of them in there. And I'm going to show you how to do this with Desmos in case you're like, there's no fucking way I'm going to be able to do that. And you might be thinking that. But that's okay, you'll have Desmos on your side. And Desmos makes this really fun. Whoa, that's pretty bad. So let's go back over here and see, is that right? And you can kind of see, watch this, as I try to like move perpendicularly through, I've got to make sure the intersection's always perpendicular, right? So notice that if I even tried that by hand, it would work out. Isn't that cool? That is so much fun. So when you do this, if you did this with all the values of c that were possible, you'd have created what's called a geodesic. It's a collection of lines that are always orthogonal whenever they meet. So it's kind of like a map in some ways. Yeah, and you could do this like some of the maps of the Earth, like the Decatur map and those different things. They use maps like this to keep things orthogonal. All right, your turn.
It's kind of like longitude and latitude.
What's that?
It's kind of like the longitude and latitude. Like
those lines around the Earth, the longitude and latitude,
Yeah.
like they form similar structures like
Yes, exactly, yeah. Anthony, yeah.
Yeah, so after we solve the differential equation, like, did we always put it in terms of C or in terms of Y?
So for the families, I would just like, a lot of times they're just gonna be, yeah, that's a good question. So a lot of times these things are gonna turn out to be just implicitly defined, and they're more understandable that way. So I would say leave them in the way that makes them the most intelligible. In fact, don't ever worry about solving for Y unless it's super obvious. Let's just make that a law. Here's a new law for us. All right, so let's start off pretty chill. What does that family look like? Why don't we just take a minute and hone our graphing skills, or at least buff them up a little? What does that family of curves look like? And then once you're done, go ahead and find, find the governing differential equation first, and then we'll talk. Oh, that's okay. What were you thinking? What was the other one? What'd you get? Oh, you're still doing that. Okay, yeah, that's cool. I appreciate the touch of the detail. What does this family of curves look like? If you're doing algebra to rewrite that thing, don't be afraid to like absorb things into C. I see Vivian could absorb some things into her C, if she wanted. Yeah, you should be getting lines. These are just x's to the first, y's to the first. You should recognize that as a linear expression. And then I would just rewrite it like this.
You wouldn't divide C by that too? Like, it wouldn't matter?
You could, I mean, if you want to do that, Nathan, no problem. That's also good. Yeah, oh, well, easy, yeah. Totally cool. Because when you differentiate, what's going to happen anyway? When I differentiate either of these expressions, that constant's going to go away. So we'll be cool. We'll be safe.
Is that y prime equals 1/4?
Yes, thank you. It is. Yes,
So, I don't think we have to do this step because it's already.
that is correct for this one. Yeah, absolutely.
The third step is solve original equation.
So we don't have to do that one either. Yeah,
Okay,
that's good
so
stuff.
Then
we've done
We
that
just
too.
have to take, so we can skip.
Yes, we can skip, yeah,
So
exactly.
number
There's a lot of steps that are skippable here. As your maybe you're seeing, or hopefully not getting too hung up on. When you're ready to look, I do have the perp system up here.
Do you mark it a little?
I like doing it, but you know, you can do whatever you want. That's just like, it keeps me, it's when I look at it, then I'm like, I know what that means. Yeah, yeah. Is this making sense? And it does make sense, right? And think about what Olivia told us about just slopes of lines, right? If these lines all have slope of quarter, then the perpendicular family probably should be lines with slope -4. And that's what'll happen here. As soon as you integrate, you just get a bunch of lines of slope -4. And this is the y-intercept. So you take your first one, and then there's another one. There's a higher y-intercept, there's a lower y. Yeah. Just imagine things better than they are. So that's my perpendicular. So nice to see that in this simple example. Is there anything we'd like to talk about here? Because I've got, this is like warm up. But it's also kind of got some interesting things in it. As Hans was noting, you didn't have to do all the steps necessarily. So you might not do all those steps. They might not be needed, especially that eliminate C. That's not always needed. But it will be in this one. This, I was just like screwing around in my office making up a bunch of these, like just solving them and then graphing them and like, oh, it's so beautiful, look at that. So I've got some things to share. Ooh, here's a good one. Let's do this one. This one isn't quite. Shit, I don't know. Oh, here, I'll give you here's some verbiage. So here's the original family. Let's see what we can do with this. It is lines again, but it's a little more complicated. Family is straight lines, as though there were other kinds, I guess. There are. Straight lines with slope and y-intercept equal. So you have to create the parameterized family. Let's do that first. Create a family of curves where that is true for every curve in the family. And we'll find the orthogonal family.
You saying like the slope and y-intercept equal each other?
Yep. So if I have the line with slope with y-intercept 1, it has slope 1. The one with negative -1 is its intercept. I think you already got it, Kendra. Yeah. Why don't you knock it out now? Go for it. And I mean, friends, don't forget the basics, right? That equation goes a long way. So if you know this is y, this is your slope, this is your y-intercept, this is our family here. So now it's going to get a little more interesting because who knows? I don't know the answer to this. I'm just very excited to see. Sometimes I bring stuff in I don't know the answer to, and we get like that number 4 that we spent the whole class on. I think we'll be okay. And then we'll pull up Desmos and confirm. I also learned a few Desmos tricks while I was screwing around in my office too, so we're gonna have a lot of cool stuff. trying to understand what this family looks like, just keep in mind that when x equals -1, y equals 0, no matter what the curve is in that family. So they all go through -1, 0. Oh, it's gonna be exciting. You getting somewhere with it. Yeah. That's not quite that. Oh, now you gotta eliminate the c, so now solve the original equation for c. That'll start to make things a little bit spicier, for sure. And before, actually, so, Olivia, just before you go to the perp family, don't forget to get this one entirely in terms of no C's. So before you do the inversion here, solve this for C, right? And so to help you see what that might be, this would be the first move. Then you can solve for C. Plug that in there, and then you get something more interesting. Looks like you're already done. Do you have the family, the orthogonal family? What happened to that X stuff? Where's it? Oh, it should be, it's missing there.
Oh, yeah.
That's it, okay,
Yeah.
there we go. So then my challenge to you is, what does that looks like without graphing? Without like Desmos? Can you figure out what those are?
Like drop.
Yeah, like
Okay.
get a canonical form, think quadratic form. Yeah, that is.
Fascinating.
Yeah, and if you get it.
It's so boring.
Me?
All sorts of improved skills and see what we got here.
That is it.
Oh my
That is it. What is that form? Yeah. See, I think there's a line. Let's see. Oh, yeah, it'll work out. Okay. Yep. Yes, what does that look like? That is the question. Therein lies the rub. Let's see what we got. So, okay, good. Okay, you're good. So now, take that C and plug it in here. So now you rewrite your differential equation. So you got your y prime equals C. And now you solve the original for C. So you can rewrite this as y prime equals y over x plus 1. Does that make sense?
Yes.
Yeah, and then solve that. Feel good? Feel good? Yeah, it is. We got that canonical form. Actually, I should put it like this. That's just an ellipse with the center at x naught, y naught. With major x-axis 2a and then 2b for the other. So this looks like this. There's a center here. Move out a units this way. Move out a units this way. Move up b units. Move down b units. Get an ellipse. But you gotta get into that form to understand what the ellipse looks like. clearly ellipses are gonna be part of this, I'd say. Since we're talking about that, so let's see, so we get y prime equals y over x plus one. So how are we feeling about getting to here? Any questions on getting to the root differential equation? Seems like we're okay, all right, so your y prime perp is going to be negative x plus one over y, which is wonderfully separable, right? So that becomes y dy. We'll lose the perp at this point, and then minus x plus one dx. Is this all looking good? Yeah? Integrate. I would, at this point, multiply through by 2 to make life a little easier, right? I mean, take advantage of that c. You're probably worried about that, but that c can be anything. So if I make it 2c, that can also still be anything. It's totally cool. So you make this a lot better on your mind by doing this, minus 2x. And then get everything, you hope, at this point, I hope you would see, you might not, but that this is a quadratic. This is a circle kind of thing. So I've got x squared plus 2x, I'm gonna leave a little space there, plus y squared equals c. This is going to be x plus something squared. And that's gonna give me a different center. If you look up there, it's kind of like this, except we've got a equals 1 and b equals 1 down here. So this is going to be, I'm going to add a 1, and I have to subtract a 1. Whoa, shit, easy. I have to add a 1 to both sides, I guess is what I'm saying. That's what I meant. So I added 1 here, added 1 to this side. I'm just going to suck that into the c, it don't matter. This is going to be x plus 1 quantity squared plus y squared equals c. This is a circle of radius square root of c, as long as c is, again, c has to be greater than or equal to 0 here, otherwise this doesn't have any solutions that are real. It's a circle with center where? -1, 0. Yeah. It's a circle with center -1, 0. And that makes sense. Look at the original curves. These are just like the spokes on a wheel. So it works out, all checks out. Let's do one more, talk about Desmos, and then maybe even call it an early day, unless you want to hang out and work on stuff, whatever. I got one last one. This one's just so cool. It's just so neat. Because I've never seen this crazy ass curve before, but could you just do this all for me for that one, please? I'll start getting stuff on Desmos. I was just mesmerized by this. And then I'll give you some fun ones you can work on too. Right? You can probably hang out and just keep working these. You can do whatever you want, I guess, really. This one works out it's kind of cool what happens when you eliminate the parameter. I'm gonna run to the restroom real quick. I'm gonna forward your answers when I get back. one thing I would, well, let's see. I was gonna say I wouldn't absorb things into that C there. Yeah, I probably wouldn't absorb things into this C. I don't know, I'll work it both ways, because I feel like I'm giving you conflicting information on that. Yeah. Let's see what happens. Let's see. So then you sub this C equals y over 8x cubed. Yeah, I don't think I'd absorb things in on the way down to the differential equation. I feel like that might lose some good things. It's when you're solving it, then feel free. When you're going up, feel free to absorb. But I think in this direction, absorbing things will lose something vital like that 3. So this is just 3y x squared. Yeah. Yeah. Cool. Cool. Good work. You got that. Yeah, I think that 3 is vital here. No, maybe not. No, maybe. I don't know. I'm gonna do it the other way on my own. Is this looking like what you're all getting? Something like this? Yes? Okay, cool. So that's kind of hard to understand, right? That's when you need Desmos. And honestly, that's fine. Leaving that like that is great, because I don't know what the hell that is. It doesn't get any better if we, solving for y would suck, because then you'd have to do a plus minus root. I think the only thing I would do here, if I wanted to like make this make more sense, is solve for x in terms of y. We're not used to doing that, but it can sometimes be informative. So let's see here, so we got 2, so we really have this. This is 2 over 3x, and that's gonna equal y squared minus c, but now I'm going the other way, so I'm absorbing things into my c with abandon. And then this is, you're gonna flip both sides, and then multiply. No, I'm starting. Let's go take a look at Desmos. Because when C is negative, then you've got asymptotes. When C is positive, you've got other good things. It looks like there's no restriction on C up there. So let's see, so we just get 2/3 y squared plus C like that. You know, what the hell is that? Who knows? I kinda have an idea, but let's take a look. That's not working, so I'll try this. That sounds good. That sounds reasonable. So mostly I want you to see the original family. Like I was just like in my office like, I've never seen these curves before. They're amazing. But yes, just the lights. I'm sorry, yeah. Thank you. Yeah, I wasn't very clear there. Look at that. This is the original family. Isn't that crazy? I've never seen those before. Quite beautiful. Let me show you what I did learn about Desmos. Instead of putting, so you could put a parameter here if you want. You put like a C and then it says add a slider. And that's one way to understand these families. But here's the thing I learned. You can actually, instead of a constant, you can pass it an array of values. So let C be -5, comma, 1, 2, 3, on up to 5, like that, put those in brackets and it plots all of them. Desmos never ceases to give amazement and joy to our lives. So that's our original curves. And let's take a look at this, and we're just entering it implicitly here. So, and we'll parameterize this one. So this is going to be y squared equals 2/3 over, I guess that's 2 over 3x, right? And then plus c. And then hit enter. Ah, look. So the blue curve is the, and that looks orthogonal, doesn't it? So look, no matter what, no matter what, everywhere they cross is perpendicular, even there. So there's the like, C is negative. Yeah, so. Is this not amazing? It's so simple. And like now you have access to like the engines on these functions. You can get in there and like rip them apart and rebuild them in your own way. Let me show you one more. And so this will be a problem. I'll leave this for you. Here's a challenge problem. Here's your family of curves. It's going to be C. This one I had fun with too, so you need to have as much fun as I did. C times e to the sine of x. And let's see, what does that look like? Is that the one? Is that the one I was doing? Let's see. Yeah. Yeah. And then find the orthogonal family. Who could even know? I don't even, what could it be? The answer is really cool. That's the answer. So, that's all I have to show you for today. Let me give you some stuff to practice with. And we can hang out here and work on it if you want. Or you can leave. We could call it another day. Do whatever you want. I won't judge you. Call it an early day. It won't make my life unhappy at all. Let's see, so what are the problems? So these are for you, friends. And I will write up full solutions to these. But the way to check is what I just did. So create your orthogonal family, get on Desmos, plot both families, and then see if they look orthogonal. You're going to know right off the bat if you got it right. So here are yours. And these are nothing, there's no more turn in because we've got an exam next Wednesday, so I'm not collecting any more shit. I got stuff I still have to get back to you, so I don't want any more to grade. But let's see, y squared equals cx cubed, x equals ce to the y squared. Here's a weird one. Right? Like what? And then we did one, so that one's already done. Oh, here's a fun one. Circles through the origin. That means they have the origin as a point. Circles through 0, 0 with centers on the x-axis. Doesn't that give you chills? Kind of. I hope so. So that we have things like this. So you got circles that look like this. They all look like that. How do you make those? How do you make those? So that's part of the problem. Create a parameterized family that looks like this. Now this looks like serious lines of force, right? Little magnetic point right there, and all those equipotential lines rolling around. And oh yeah, I got a couple more. So then x squared minus y squared equals c, family of hyperbolas. C can be positive or negative here. When C is positive, they look like this. When C is negative, they look like that. So you get a whole bunch in the plane. Fill the plane up with them. And then how about one more? X squared minus y squared equals cx. That is so much, you don't need any more. That's a lot of fun, right there. So we can hang out and just work on these, I'll be here to consult. Oh, we got 15 more minutes anyway, so. You can leave too if you feel like it. I hear zippins.
I know what that means.
I've been around. I've also been in a lot of places I wanted to get the hell out of, so I get it. I hope you don't want to get the hell out of.